this afternoon. So if we take a look at the do now, number 1 says for a second order reaction. So for a reaction that is second order, what plot will give us a straight line? So for a second order reaction, I want to know what plot will give us a straight line. So I'm going to actually just answer them on the whiteboard behind me. So if you need to pin me to your screen, if you need to go back and forth and pin me to your screen to make it nice and big, you can. Just hover over my picture and click on the pin. Or you can just like zoom in, look really close. So for number 1, for a second order reaction, so you're thinking about which graph will give the straight line if it's second order. So it's telling us it's second order. The plot of 1 over the concentration versus time will give us a straight line. Right, the 1 over concentration versus time will give us a straight line. So that's how we tell that something is second order. If 1 over concentration versus time gives us a straight line. For number 2, for the reaction whose rate law is given above, a plot of what would give a straight line? So they gave us the rate law. They told us rate equals K times the concentration of A. So they gave us the order. We just have to figure it out first, right? Because if we're looking at what plot will give us a straight line, we need to know what order of the reaction it is. So we need to look at the rate law, right? We can tell the order based on the exponent that's up here. So if there's no exponent here, it's assumed to be a 1. So this is first order. So use the rate law to figure out what the order is. If it's first order, we have to think about what would give a straight line. The one that would give the straight line is the natural log of concentration versus time. So second order is 1 over concentration versus time. A first order process is the natural log of concentration versus time. And then number 3, how can we find the rate constant for the rate law above using the graph? So for number 3, how could we find this value of K using this graph? So if our graph looks like this, it's time, ln of concentration of A. It wants to know how could we find the rate constant? Well, to find the rate constant, remember that the slope is equal to the rate constant. K needs to be positive. So if you can read this, it says slope equals negative K. Because this is a negative slope, K always has to be positive. So to answer number 3, we can say find the slope. And I'm going to make a reminder that says K is always positive. So if you get a negative value for K, make it positive. You get a negative value for K, make it positive. And then finally, number 4, if the rate constant K for a first order process, okay, so the rate constant for a first order process, so K is 0.543 per seconds, what is the half-life? Now, before we solve for the half-life, I do want to make a note here that even if it just said, if the rate constant is 0.543 per seconds, what is the half-life? So if they didn't actually tell us that it's first order, you can figure out that it's first order based on the units. Remember, you need to know the units for K. So if it's just per seconds, a first order process is always per seconds or per whatever your time unit is. So that's another way to tell that it's first order. So half-life, remember you have the half-life equation on your equation sheet for a first order process. The half-life is 0.693 over K. So the half-life equation is 0.693 divided by K. So if I put it in my calculator, right, so we'll do 0.693 divided by 0.543 per seconds. So 0.693 divided by 0.543 is 1.28. So T1 half is 1.28. Now, T is time. So if I have nothing over per seconds, that results in our unit just being seconds. So the half-life of this process with a smaller rate constant is 1.28 seconds. That means every 1.28 seconds, we use up half of what we had before. Okay, so again, 1 through 4, I worked through up here. So make sure that you have each of these written down. 1 and 2, again, are looking at the plots. You have to be able to tell which plot or which graph will give you a straight line. And then 3 is thinking about slope. And then 4, can you calculate the rate constant when you're given a graph. So during class today, I'm going to start by going over some questions about mastering. So there were 2 specifically that I got some questions about yesterday. So we're going to go through those, and then we'll do some examples. So we'll do examples 19 to 22. 19 and 20 you'll actually do in breakout rooms. So as you were working on the do now, I was trying to separate everyone into breakout rooms. When you're doing those 2 examples as a group in breakout rooms, there's 4 to 5 people in a breakout room. You don't have to turn your video on, but it would be very useful if you even unmuted and just kind of talked about it, almost like you were in class. So once you go into breakout rooms, unmute, talk as a group, and then answer those questions. And we'll talk more about that when we get into the examples. Then you'll be able to work on mastering. So based on video 5.4, those are questions 36 to 45. They're not all worth points. Right? A lot of them are practice or extra credit. And then for tomorrow, you'll watch video 5.5. There are only 6 videos, so we're almost to the end of kinetics. As you are working on mastering or you're reviewing your notes, please keep in mind that the textbook is going to be a very good resource as we're getting into all the new material. So whether you have a hard copy or you use the e-text on mastering, or in Google Classroom, I also posted a PDF of the hard copy of the textbook. So use that, refer back, look at some examples, things like that. Or I have additional resources on the class website. So ptapchem.com, I have additional resources there that you can use as well. So as we look at mastering, so these were the 2 questions that I was sent yesterday with just kind of some general, like, how do we start going about these questions? So we're going to start by looking at 31, and then we'll look at 33. So for 31, they give you a reaction, and they tell you that it's first order. So that's really important. Remember to look off to the left side. They give you diagrams, information, things like that over on the left. So this tells us that it's first order. And then it says using the data, determine the magnitude of the first order rate constant. So this is like example, let me find it in the notes. This is like example 17 and 18 in the notes packet. Now 17 and 18 were second order processes, but it's the same thing. You do the same thing as if it were first order. So we know that it's a first order process. They tell us that. So to determine the rate constant, we have to look at the slope of the line that is linear, right, of the graph that is linear. And so if we have time versus pressure, remember pressure can be used interchangeably with concentration when we're dealing with gases. And so if we have time versus pressure, just figure out the natural log of pressure and then figure out the slope. So if you figure out the natural log of even just the first and the last point, like we did in example 17 and 18, if you take the natural log of 1 and the natural log of 0.803, there are your y values. And then you use the time for your x values. So you would do y2 minus y1 over x2 minus x1. but the y values have to be the natural log of pressure. 33 is going to be similar. So 33 asks you what the order is first. So you have to actually figure out what the order is. So since we don't know the order of the reaction, we have to start by plotting. We have to graph. If it's first order, we would graph natural log of A versus time. And if it was second order, we would do 1 over moles versus time. Normally we would do concentration, but they didn't give us a volume, so we just have to use moles. So when you have natural log versus time, make a graph. Whether you want to make the graph in your calculator or you want to use Google Sheets, make a graph of moles versus time, or sorry, make a graph of ln of moles versus time and 1 over moles versus time. Whichever one gives you a straight line is the one that that's your order. And then to find the rate constant, you just need to find the slope of that line. So if it's first order, you'll do ln of moles and solve for slope. If it's second order, you'll have to do 1 over moles, find your points, and then find the slope. So 31 and 33, you have to do like what we did in the examples where you have to take the natural log or you have to take 1 over in order to find the slope. Any questions on those? There were other ones that were similar, but those were the two that I had questions on. All right, so then if there aren't any questions, we're going to just jump into looking at information from video 5.4. So video 5.4 brought back in the collision model. So that's why it says the collision model again, because we've talked about the collision model before, right, when we started kinetics, but now we're going to bring it back up again. So remember that rate. So a rate of reaction is affected by concentration and by temperature. More specifically, the rate of reaction is affected by concentration of reactants and temperature. We can talk about how the collision model affects rate. So collision model just means that in order for molecules to react, they must collide, right? The collision model. So if we think about the collision model, molecules must collide in order to react. And the greater number of collisions, the faster the rate. So those are the two kind of premises behind the collision model. They must collide, and the more collisions, the faster the rate. Now, what that means is when we think about concentration, the more reactant molecules we have present, the more collisions there will be between the reactant molecules and the faster the rate. And then when we think about temperature, the higher the temperature, the faster the molecules move, more often they collide, the faster the rate. However, and this is bolded, underlined, not all collisions lead to products. So just because there are collisions occurring does not necessarily mean that we will form products. Really, only a small fraction of collisions lead to products. So before we thought about, okay, as long as our reactants are colliding in some way, we're going to have products formed, but that's not necessarily true. We need the reactant molecules to collide with two important things, right? Two important factors. They need to have the correct orientation and they need to have enough energy. So in order for a reaction to occur, reactant molecules need the correct orientation and with enough energy. And that's called activation energy. The activation energy is the energy needed for the reactants to react and form products. So this bottom part of this slide is really, really important. You need proper orientation and energy for what we call an effective collision. Now, orientation is really based on what your reactants must do to turn into products. So if you have something that you're forming, NOCl is always a common one. You have NOCl colliding with, let's say, oxygen, O2. Well, if your reactants are NO2, right, that means that we need the nitrogen portion of NOCl to collide with O2. Right, so it has to collide with O2 in order for that part to bond and form something new. If the chlorine hits the O2, that's not forming NO2 like we need. So they need the correct orientation and they need enough energy. So that's big for the collision model. So what I'm actually going to have you guys do is I'm going to have you guys do examples 19 and 20 in breakout rooms. So I already have you split up, but I'm just going to kind of talk through each one. So example 19, you're using the collision model to explain two different things. So remember that the collision model is that molecules must collide to react, and the greater number of collisions equals a greater rate. So you're going to be using the collision model for example 19, and then example 20, I want you guys to try with your groups as well. So with example 20, A is are things that we've talked about before. So you're determining the order using the data. So notice it's concentration versus rate. And then I ask about OH minus, and then part B is looking at the particle level reasoning. So that's looking at the collision model. So I'm going to put you guys into breakout rooms. I'm going to give you guys about, let's say, 5 minutes to go through examples 19 and 20. So we'll do examples 19 and 20. And I'll go ahead, I'm going to set the timer for 5 minutes. So it'll end the breakout rooms at 5 minutes, bring you back here. Please, 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 please talk to each other, right? It's not going to be worth going into breakout rooms if everyone's muted. So unmute, talk to each other, ask each other questions, just like you were in class. Okay, so I'll go ahead, I'll open the rooms, take 5 minutes, answer examples 19 and 20. Okay, so hopefully you got at least part of number 20. So hopefully you got 19 and part of number 20 answered. But most of these examples are old AP questions. So again, just more practice with timing. So 19 had you look at two different reasonings for why reaction rate would increase. If it says use the collision model, make sure that you are using the collision model. So you're saying that molecules are colliding and you're explaining how whatever they're telling you in the problem affects the number of collisions. So if we look at part A, it wanted us to use the collision model to explain why increasing concentration of a reactant should normally cause the reaction rate to increase. So according to the collision model, molecules must collide with each other in order to react. The greater the number of collisions, the greater the reaction, or I should say the greater the reaction rate. When reactant concentration increases, we're increasing the number of reactant molecules, the number of collisions increases, and this leads to a faster rate. So you didn't necessarily have to say according to the collision model, but College Board does like when you talk about how you're justifying. So since you're using the collision model, if you just give a quick, according to the collision model, here's what must happen. But the biggest thing with this, remember that this is concentration of a reactant. Product concentration does not affect the reaction rate. You can calculate rate using product concentration, but the concentration of the products does not affect how fast the reaction occurs because you're thinking about reactant molecules colliding to form products. So part B wants us to use the collision model to explain why increasing the temperature causes the reaction rate to increase. So at a higher temperature, molecules move faster, which leads to an increase in both the force and collisions, the force of collisions and frequency of collisions. So hopefully that sounds familiar to when we did gases and we talked about pressure. That was based on collisions as well. So higher temperature increases the force and frequency of collisions, which leads to a faster rate. So you're always bringing everything back to the number of collisions. If we look at example 20, so example 20, you can actually tell based on that table up at the top, this was part of a free response question. And so this is in an experiment. A student studies the kinetics of the reaction represented below and obtains data in the table. So using the data, it wants you to determine the order with respect to S8 and justify your answer. And then it wants you to actually calculate the value of OH minus that was used in trial 3. So now instead of calculating a rate, we're actually calculating a concentration. And it says considering that the reaction is first order. So they're actually telling us what the order of OH minus is. And then it wants us to justify our answer. And then part B says that the next day, using the same concentrations, the reaction occurs at a much slower rate. The student observes that the temperature is lower, and so provide 2 explanations that help to account for the fact that the rate was slower. So let's start by looking at part A. So when we look at this top table, when we're figuring out the order with respect to S8, we're looking at how S8 changes while OH remains constant. Because remember, you only want to change one at a time. So S8 triples. The rate also triples. 0.1 times 3 is 0.3. 0.699 times 3 is 2.10. So when the concentration is tripled, the exact same thing happens to the rate. And so we would say that the reaction is first order with respect to S8. So for part 1, the order of S8 is first order. Our justification is just this. When the concentration of S8 triples, the rate also triples. That's a fine justification. And then part 2, determine the value of OH minus that was used in trial 3. So if we know that OH minus is first order, I'm going to look between trial 2 and trial 3 because that's where S8 remains constant. Now, after I talk about this way, I will talk about another way that you could solve it. It would be a little bit more work, but I'll explain the other way. So if it's first order with respect to OH minus, that means that whatever happens to concentration also happens to rate. So if we look at the rate, 2.1 to 4.19, the rate actually doubles. So if the rate doubles, that means that the concentration must also double. So 0.02 molar. So again, whatever happens to concentration also happens to rate. So if the rate doubles, OH minus must double because S8 is remaining constant. Now, another way that you could solve this is you could write out the rate law. Rate equals K times the concentration of S8 times the concentration of OH minus because they're both first order. And then you could solve for the rate constant. So using trial 1 or trial 2, you could solve for K. And then you could use that. So rate equals K times S8 times OH minus. And you could actually plug in rate S8, your value of K, and you could solve for OH minus. And you should get the same thing. It might be rounded a little bit differently, but you should get the same thing. And then for part B, so your 2 explanations. Now, this was from a free response question. To me, these are very similar in reasoning, but I guess they're just different enough that College Board thought that it was 2 separate explanations. So we are providing 2 explanations that help account for why the rate is slower. So first, the temperature was lower. So the average kinetic energy of the reactants was lower. And so that means that there were fewer collisions between particles that had sufficient energy. So that means that fewer reactant molecules had the necessary energy. That's the activation energy. So your first explanation could say that fewer reactant molecules had the activation or were able to meet the activation energy. Because if they have lower energy, that means that they're not going to hit that activation energy barrier in order to react. And then number 2, since the temperature was lower, the kinetic energy was lower, the average speed of the particles was lower. And so at lower speeds, the reactant particles collide less frequently. So really your 2 explanations is number 1, they don't have the energy needed to overcome activation energy. And number 2, they're colliding less frequently. So those are the 2 explanations that College Board was looking for. Any questions on examples 19 or 20? Right, so then we're going to move on to the next kind of set of examples. So when we're looking at temperature, I'm going to go back and kind of talk about activation energy that we just talked about in example 20. So at any particular temperature, molecules have average kinetic energy. Just like when we talked about gases, temperature is average kinetic energy. Now, again, that's average. So at 25 degrees Celsius, there's an average kinetic energy, but some molecules have less energy than that, and other molecules have more energy than that. And so if you remember when we talked about gases, we talked about the Maxwell-Boltzmann distribution, and this is also in your notes. And so this is where we can see how many molecules have a certain kinetic energy. So at a lower temperature, notice that more molecules have a lower kinetic energy. At a higher temperature, there's a higher average kinetic energy, but more molecules also have higher kinetic energy. So this minimum energy needed for a reaction, that's the activation energy. So molecules that have energy that's equal to or greater than the activation energy are able to react. They can overcome this energy barrier and form products. But the activation energy, that's the minimum energy that reactants need in order to collide, react, and form products. This, and I'm trying to put the important things in these boxes on the slides. So at a higher temperature, more molecules have the energy needed to react, and so the rate is faster. All right, at a higher temperature, more molecules have the minimum energy. They're able to meet the activation energy, and so the rate is faster. Now, the last part of what we're going to talk about is looking at the Arrhenius equation. So I'm going to talk a little bit about the Arrhenius equation, but then I'm going to tell you what you need to know from this equation, and then we'll get into a couple more examples. So the Arrhenius equation is looking at how rate constant is affected by activation energy. So the Arrhenius equation is really based on three factors: the number of collisions per unit of time, the fraction of collisions that occur with correct orientation, and the fraction of molecules that collide having energy equal to or greater than activation energy. So the Arrhenius equation itself looks like this. So K is the rate constant. A is what we call a frequency factor. So that's related to the frequency of the collisions and how many collisions will occur with correct orientation. This E, that's the inverse natural log. EA is activation energy. R is the energy ideal gas law constant, 8.314, and T is temperature in Kelvin. Now, are you going to have to do any calculations with this? No. You are not going to have to do any calculations with this. I'm showing this to you in case you use this in the future, but I want to be able to look at this equation and point out what we are going to focus on. So we have K, which is the rate constant, and we have activation energy. So we know that they are related somehow. So a more useful version of the Arrhenius equation, and we used to do this in lab. We will not get to this year. But when we look at the Arrhenius equation, we can actually plot the natural log of the rate constant versus 1 over temperature. So when we want to use the Arrhenius equation, we can actually plot ln of K versus 1 over temperature. And the slope of that line is equal to negative EA over R. So if we have the rate constant and we have the temperature, we can actually calculate the activation energy. Now, again, do you have to do calculations with this? No. But on the slide, here's what you need to know. So I would recommend maybe writing this down somewhere in your notes. So as the activation energy decreases, so that means you have a smaller and smaller energy barrier. The reaction will proceed faster because less energy is required for molecules to react, and the rate constant increases. So the faster the rate, the larger your rate constant. So again, the faster the rate, the larger your rate constant. So as activation energy decreases, K actually increases. So as you have a smaller activation energy, you have a faster rate and a larger rate constant. If you have a huge energy barrier, so you have a very large activation energy, think about like doing box jumps, for example. Right? If you go to the gym and you're doing a box jump, so you just have a giant box that you have to jump up onto. Well, if it's a small box, I have the energy needed to jump up onto that box. If it's a huge box, I'm not going to have the energy needed to jump up onto that, which means it's going to take me a lot longer to jump up onto that box. That's a larger activation energy. It takes me longer, so it's a slower rate, and therefore it's a smaller rate constant. So as activation energy decreases, the rate constant increases, or the other way around. As we increase the activation energy, we decrease the value of the rate constant. So that is what you need to know. So what do you need to know based on all of this Arrhenius equation? You need to know what is in this box. You do not need to do calculations with the Arrhenius equation. You just need to know, how does the rate constant relate to activation energy? So the smaller the activation energy, the larger the rate constant, the faster the rate. The larger the activation energy, the smaller the rate constant and the slower the rate. Okay, any questions on activation energy and rate constant for now? All right, so then the last thing we're going to look at before we get into the two final examples is I want to review reaction energy profiles. So these are also called reaction diagrams or energy diagrams. If you flip to page 17 in your notes, page 17 in your notes, you have this. You do not even need to write this down. You already have this all written out in your notes on page 17. It's just that this diagram is on the left side, the important information is on the right side. So these reaction energy profiles, or these energy diagrams, these show us the energy of the reactants and the energy of the products, which allows us to look at enthalpy, which is delta H. Right, so enthalpy is delta H. Remember, that's telling us if it's exothermic or endothermic. This shows us the activation energy. So the activation energy is the energy needed to get from the reactants up to the transition state or the activated complex. And then we can see how hard is it for reactants to become products. So the activation energy for the forward reaction, so forward reaction means reactants going to products, is the difference between this peak and the energy of reactants. So that shows you right here, the activation energy is the energy of the activated complex. So whatever energy this is up here, minus the energy of reactants. That gives us this activation energy. The enthalpy of reaction, so delta H, is the difference between potential energy of products and reactants. So you're looking at, to get from reactants to products, do we have to gain or release energy? So in this example, the products are lower in energy. So reactants have a certain amount of energy, products have less energy than that, which means the reactants must release the energy. So if the potential energy of the products is less than that of the reactants, it's exothermic. So the reactants will release energy. If the potential energy is more, so if the products were actually up here, that means that the reactants would have to gain energy to become products. That'd be endothermic. And then down here, as activation energy increases, the reaction rate decreases. So this peak, right, the higher this peak becomes, the greater the activation energy. Well, that means that the reaction rate will decrease because more energy is needed for the reactants to overcome that barrier. Now, there was a question on what if your reactants and your products have equal energy? If they have equal energy, it would be neither exothermic nor endothermic. We don't usually see them having equal energy, but if they did, then we would say it's neither exo nor endothermic because the energies are equal. We will always be looking at either exothermic or endothermic. Okay, so again, all of this information on this slide is on page 17 of your notes. I just wanted to talk about the reaction diagrams or the reaction energy profiles. So now we're going to look at example 21 and 22. So these are the last two questions, last two examples that we'll look at, and then you'll have time, almost a whole period, to work on mastering or to watch the video for tomorrow. So example 21 says, consider a series of reactions having the following energy profiles. So we have reaction 1, 2, and 3. Part A says, assuming that all three reactions have nearly the same frequency factors. So what that means by having the same frequency factors is that the number of collisions are essentially the same. So that means that assume that the reactant concentration is the same and the temperature is the same. So really what that means that we're looking at is the activation energy. So rank the reactions from slowest to fastest. Okay, so if they have the same concentration and they have the same temperature, then our reaction rate is based solely on the activation energy. So the activation energy is this peak. So the smaller the peak, the easier it is for the reactants to get over that peak and become products. So we're ranking it from slowest to fastest. So the slowest is the one that has the highest activation energy. Like the slowest reaction is the one that has the largest activation energy, because that means that it's more difficult for the reactants to overcome that barrier and become products. It's going to take longer for them to overcome that barrier. So if we rank them, right, the slowest is the one with the highest activation energy, which is graph 2. The fastest is the one with the lowest activation energy, which is graph 1. So I want to point out the difference between graph 1 and graph 3. So the activation energy is the energy from the reactants up to the peak. So in graph 1, reaction 1, the activation energy is 15 kilojoules. Reaction 3, we're going from the reactants all the way up, that's 20 kilojoules. So the slowest is reaction 2, then reaction 3, then reaction 1 is the fastest. So again, we were ranking from slowest to fastest. Part B, what does the rate of reaction depend on? So this is just a conceptual question. So part B, what does the rate depend on? Well, the rate of reaction depends on the reactant concentration and the temperature and activation energy. So again, the rate depends on the reactant concentration, not just concentration. It has to be reactant concentration and the temperature/activation energy. The lower the value of the activation energy, the faster the reaction. So a low value of EA, so like in reaction 1, a small activation energy means that it's relatively easy for reactants to convert to products. So in reaction 1, it's going to happen the fastest. So part B, rate of reaction depends on reactant concentration and the temperature/activation energy. Right, so then we have part C and D. So part C, I'm going to just kind of read part C off while some people are finishing writing. So part C, in terms of activation energy, explain why the reaction rate tends to increase at higher temperatures. And then part D, which reactions are endothermic. So part C is a really important question. So I want you to star part C. I want you to put a star next to part C, because part C is important for answering conceptual questions on the AP exam. So in terms of activation energy, so that means that you have to talk about activation energy in your response. So in terms of activation energy, explain why the rate increases at higher temperatures. So the kinetic energies of the reactants are distributed, right? And if you don't have that part, that's okay. But the kinetic energies are distributed over a wide range. But we always have an average kinetic energy. At a higher temperature, the average kinetic energy of the reactants increases. You have to have that written down. At higher temperatures, the average kinetic energy of the reactants increases. This means that more molecules have enough energy to overcome activation energy. This leads to a faster rate. So I'll say that again. At higher temperatures, the average kinetic energy of the reactants increases. This means that more molecules have enough energy to overcome the activation energy, which results in a faster rate. So the more energy the reactants have, the more likely the reactants are to overcome that activation energy barrier, and the faster the reaction will be. And then part D just wants to know which of these are endothermic. So endothermic, you're thinking, which of these do the reactants have to absorb energy to become products? So if you take a look at each of these potential energy diagrams, in order for it to be endothermic, the reactants have to gain energy, right? Energy must go into the reactants to form products, which means your products have more energy. They also helped us in this because they told us this is -10, this is -15, this is 5. Well, negative delta H's result in exothermic processes. So which are endothermic? Endothermic reactions are those that require energy, so a positive delta H. Only reaction 3 has a positive enthalpy. So reaction 3 is the one that is endothermic. Right? Any questions on example 21 before we go on to example 22? Last example. All right. So for example 22, gives us this reaction, Cl plus HBr yields HCl plus Br. Has an overall enthalpy change of -66 kilojoules. The enthalpy is delta H. So it's telling us the overall delta H is -66 kilojoules. So I want you to write down right underneath -66. What does that mean? If it's a negative delta H, what is that going to mean? Right? It means it's exothermic. So it's going to be an exothermic process. And then the activation energy for it is 7 kilojoules. So a very small activation energy. So part A says, sketch the energy profile for the reaction and label the following: potential energy of the reactants, potential energy of the products, the activated complex or the transition state, EA, which is activation energy, and delta E. Now delta E is equal to delta H. So if you label it as delta H instead, that's fine. And then B asks, what's the activation energy? So I want you to take just a minute, see if you can sketch the energy diagram based on this information. So use the energy diagrams from example 21 kind of as a guide, and think about how you might draw the energy profile for this reaction given the delta H value and the activation energy value. So try to draw at least what the reactants and products might look like. Which one's going to have higher energy, the reactants or the products? And then kind of go from there. Okay, so if we take a look at part A, so just sketching the energy profile. Now, I didn't put the y-axis and the x-axis, so I would have done that. But then it wanted you to label reactants and products, activated complex, right, everything. So because this is -66 kilojoules, this is an exothermic reaction. That means that the reactants are going to lose 66 kilojoules of energy. So the reactants will become the transition state and then lose 66 kilojoules. So the difference between the reactants down to the products, that's the -66 kilojoules. That's your delta H value. So it's not from the transition state all the way down. It's from reactants to products. That's the delta H value that you should label. So then the transition state is a pretty low peak here. It's only 7 kilojoules. So from the reactants up to the transition state is only 7 kilojoules. It's almost 10 times as much to go from reactants to products as it is to go from reactants to the transition state. So we have reactants, we have the activated complex. So remember that the transition state is when you've broken all of the bonds. So everything is kind of just in limbo, waiting to form your products. So you have your activated complex, you have your activation energy, which is from the reactants up to the transition state. And then you have your delta H, which is from reactants down to products. Now, I asked in part B, what is the activation energy for the reverse reaction? So the key thing here is reverse reaction. That means if I'm going from the products all the way up to the transition state, what would that activation energy be? Well, to go from the products just up to reactants is 66 kilojoules. Then to go up to the transition state is another 7 kilojoules. So the activation energy for the reverse reaction is 66 plus 7, which is 73 kilojoules. So example 22, you were sketching the energy profile, right? You were sketching the reaction diagram, which again should look like this. Reactants are much higher in energy than products. You have your transition state, your activation energy, your delta H, and then EA for the reverse reaction is 73 kilojoules. All right, so any questions on any of the examples? Quiet in the chat today. So for the rest of class, you now have basically a period to work on mastering. So you can focus on 36 to 45. Those are the ones that go along with video 5.4. For tomorrow, I posted video 5.5. So video 5.5 is looking at reaction mechanisms, which means you have like multiple steps in a reaction. We will go through those examples tomorrow. And so if you'd prefer right now during class to watch the video instead, you can do that. But whatever you choose to work on this period is up to you, either mastering or watch the video for tomorrow. And then tomorrow in class, we'll go over the examples of video 5.5. Again, if you need extra resources, use the textbook, use the class website. As always, send me questions on Remind. If you have questions on mastering or anything else, I will be back in school tomorrow. Not that it matters, you guys are at home, but I'll be back at school tomorrow. So if there are other questions, I can move around and not just have to use this whiteboard behind me. So yeah, if you have like mastering questions or anything, let me know. I'll kind of do what I did today and review some mastering. Okay, so that's all I have for today.